Welcome and good morning. So we continue flash separation unit for the ASPEN simulation. For this class unit, we have ASPEN on your computer. I have recorded it. If you later I will show it or upload it and edit. Flash separation unit. If you refer the books, it's page 99. So this is how you clean the parameter step. Since you are using acetone, water, and IBK again, we need to clean the parameter before okay. So for the NIBK, those who have the who don't who don't have the save file, can refer to page slide 37 on the introduction slide. We produce water acetone and ethyl isobutyl ketone. This is this one. This is the previous one. It's last, last week. No, yes, last week. We've done it until 3 mix. Now we continue to flash. So the condition for each stream is 50 water 25 in my case. This is okay. Right. So that is all for the first part of the simulation here. So how to clean the parameters? Under tools, this is your toolbar. This is under properties. This one, clean parameter. Here all parameters. The first choice is to remove the validity parameters that have been added to input form. There are three choice. Second choice to remove parameters that are incomplete, missing value. And the last one is to remove all, including the face memory primitives. So next is, I'm not sure if you can start with adding the stream table since this thing is gone now. We have also output text to create the property set. So a property set is a collection of the dynamic transport and other properties that you can use in physical property table. This is so this is under simulation one. So we have many short form. Example, rho mx is equal to the density of the mixture. Mx refer to the mixture. And mu mx is the viscosity, sigma mx is the surface tension. Now we will modify the export. So we will include the diffusivity value. So go to the simulation. On. So to add the steam table, just go to result summary. Then click send to flowsheet like this. Result summary. Okay. This one. Stream send to flowsheet. Check your toolbar. Send to flowsheet. Oh, actually that one. So this flowsheet is real time. If you do changes, it will change here. Back to the export. So for the export is under setup property set one. Under property set one to export. Alright. So under the export, there are only three: rho, mum, and sigma, and x. The task is to include this diffusivity value for the mixture. This is dmx. dmx. No, the mum mx unit is Cp. Sigma is di over cm. This is 20 centimeter per second. Okay. So next we must add the export property set to the stream table that is shown in the flow sheet. While simulation environment is the active mode, and using navigation pane, go to setup, record option, stream platform, click on the property set button. Doing so will open up the window. So setup, property set, record option, stream, property set, done. Property set, and find your new the export. Is a new change or yes. So now the T export have a unit for the others. We introduce a new diffusivity value for the mixture. Next is to add the stream condition. So to add the stream condition, go to the main flowsheet. If you lose the main flowsheet, you can go to view, click the flowsheet. It will appear like this. Now zoom in on your go to okay, it's already on modify, then you can choose temperature and pressure. See it appear. This is 25 degrees C, 1 atm. No? After the mixing, it's 19 degrees C, pressure still remain. Next is how to generate the report. So the report is important for when you do the assignment later on. You need to generate a report for the proof. Sometimes I read from the report just to make sure. So there are two types of report. From the properties, you need to generate one report, and for the simulation, it's one report. So you have two reports. So to do that, go to home. There's a report. Let me run this first. Okay. There are many options, several options, all lanes block. So now it's for block. We only have mixer here. But later on for your assignment, you need to report for all simulation. So the properties is the same. So the report is in text format or notepad format like this. So this is report for block mixer one. How about properties? It's the same. See the report. Or you can write this. So, okay. Okay, now we add the separation unit. So use flash tree in model palette. This is what we call a model palette. Flash tree is based on vapor liquid liquid equilibrium or VLLE and suitable to separate MIBK from water because MIBK is immiscible in water. A flash 2 is based on VLE. See flash 3, VLLE. This is flash 2 based on VLE. The goal is to separate feed into two streams and obtain 95% water and acetone purity respectively. For this case, we use flash 3 VLLE. Click, click here, flash, flash, flash 3 1. Okay. Next, you need to reconnect this. So reconnect that. There are two choice. Reconnect source or reconnect destination. Which one? Destination. Reconnect source is from here. This is the destination. This is the source. Then we have three output. Oh, wait, alamak. Gem ASPEN. Wait ah. Eh, apa lu? ASPEN ya. Yep. Oh, kalau itu Fast safe. Okay. Because yang bawa joiner. Hmm, it, set apa tu? Slide 8, eh? Because yang boleh proceed tu, kita proceed. We got some issue with the DMX, eh? The ASPEN. Oh, this one is city. This one. Okay. So one. Don't forget to say. To last second. And my BK. I know 50-50. Okay. I feel like it is. Okay. Time to flush it. Alamak. Pakai ni. 200, huh? Okay. 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 All right. Continue. So flash. Oh, dah pindah ke off. Oh, dah gitu. Hmm. Gitu. Save. For the top is FL1. Okay. FL1 vapor. Then we have FL1 H2O. FL1 NBK, yeah. Okay, so this is the latest one, flash separation. Next, so the task is to, also the goal is to separate 95% water on acetone purity using this flash tree, this flash tree. Okay, next is asking the condition for the separator, the flash separation, 50 degrees C, 1 atm. So there are 1, 2, 3, 4, 5 type of separator in ASPEN. We have flash 2, flash 3, decanter, sep, and sep 2. So the flash 2 is a 2 outlet flash. Determine thermal and phase condition, the focus. Use for flashes, evaporator, knockout drum, single stage separator, and fill water. The one that we use is the flash 3 separator. It's a 3 outlet flash. You see the outlet, there are 3 outlets. Determine thermal and phase condition, stream splitter, and bleed valve use. We have a decanter, liquid decanter. That one is for the solid stream splitter and bleed valve. Flash 3 is for the stream splitter. Decanter is for the solid stream splitter. SEP, multi-outlet component separator. It separates the inlet stream component into any number of outlet stream. So if you have 1, 2, 3, or more than that, you can use SEP. That one is for the solid stream splitter. SEP2 is the 2 outlet component separator, so only 2, like a flash 2, similar. It separates inlet stream component into 2 outlet stream. This is also for the solid stream splitter one. So each have its own purpose, depend on your system. All right, no warning. So next is to check the uh, all right, strain laser. Yes. We have a new one. PFLI and IBK H2O and VAP, yeah, VAP. So this is all under from the slash tree. Okay. So based on this, there are no flow in FL1 vapor. You see zero. But the goal is to check the gas fraction for the FLI, sorry, FL1 H2O stream. It does contain more water, but it did not achieve the target of 0.95 H2O fraction. Which one? More mass fraction. Because the goal is to get 95%. It's around 78% only. Yeah, mass fraction water. Safe. Better to say. All right. Sure, you remember later uh, we visit this process because the goal is to increase the percentage. So we need another unit operation. But before that, we do some exercise first. So for this exercise, uh, refer to slide 11. It's using metric, chemical metric units. Yes or no? Yes saja. Ya. Alright. So for this exercise, we have water. What else? One propanol. Oh, sudah one propanol. Ada. I have to use this. Oh, but no match. Salah hijau kah? Propanol. Oh, salah hijau. Oh, si nampak dah. Propanol. Oh, then apa ya? Octanol. So we have solute. Then what else? Octanol. Water solute and ethanol. This one is H2O. You must remember it. It's easy. Mm, this is based on an RTL. Here, binary unit value. Right. Next is define new property set exclusion element as alcohol. Mm, here we are ready to go to simulation now. So before we add I need to introduce a new property set for alcohol. property set. Ada alcohol. I need to introduce a new mole concentration. Mole concentration. Unit is mole per liter. For the qualifier, it's a liquid C10H octanol. Okay, I think that's all. Okay, now go to the main flow sheet. It's one, three inlet. We have H2O. What else? Solute. Solute is one propanol. Oxygen. This one is the three mix. Okay. It's a flash tree. So flash one. The name is flash one. Okay. Although this one is actually flash three. I cannot. Okay, reduce the three outlet. C80 hash is okay. And this one is push 2O is ano naman. Don't forget to say that. Now click the next button. So it asking H2O material input. This is the feed. So for the feed, for this one is 45. 51 kilomole. You see the different if you use chemical arithmetic units, the unit is in kilomole instead of mass kg per hour. This one is 25 degrees C, 1 atm. Next, for the octanol, octanol is 45 as well. 45, those 400. Next, solute 10, right? This is input for flash. For flash, it's run at 25 VPC, 180. Check if they are error. If you see all the folders turn to blue for this, there's no error. If it's error, normally the result available will be in red or in warning is yellow. Okay. Next, check the string. This on the string. Okay, there's no paper. Flash one. Oh, sorry. Calculate log KOW. Oh, yeah, log KOW. Log KOW. Zero quick. Okay. Okay. Rồi, bạn làm tập từ share the don't not sure what is the log KOW. Mm, asking for try a similar procedure and condition using different solute. But using this method, gone. Predicting the partition coefficient of solute between water and one octanol, the integration has been widely used to demonstrate chemical hydrophobic properties. Okay. So in this case, this one you can look here, chemical hydrophobic properties. We check C8, C80 facing and H2O facing. Okay. That one. Check the mole concentration. That's a mole concentration. Oh. Check. Oh, good now. Concentration. Right? Please. Right. concentration. What? Select it is to include. Okay. If it is to add to the stream report. Yes. This one. Okay. Oh, really? Okay. And the dua. Check. Hmm. Credit cockroaches. Semua ada liquid phase. Volume block. Block. Pasti. Dalam tu. Oh, ya tu. Okay. More concentration component. Ada satu. Oh. Right. More fraction to office. Ini tadi. Cukup. Hmm. Hmm. If you try using methanol, the value should be different. No? So, okay. Now we continue with the previous solution one. Yang tadi Wait, save dulu. Okay. Open previous simulation one. Yes. Hmm, yes saja lah. Eh, yes. No. Oh, right. Continue. Problem description slide 15. A mixture containing 50% acetone, 50% water to be separated into two streams, and one enriched in acetone, one other in water. Here. Mm, the separation process consists of extraction of the acetone from water into a methyl isobutyl ketone, which dissolves acetone but is nearly immiscible with water. The overall goal is in this problem is to separate the feed stream into two streams. This is the feed stream. The two streams that have greater than 95% purity of water and acetone. So you need to get 95% on water here. Resume from previous chapter by adding both a mixture and flash separation unit to our existing product line. The flash separation unit can be used to represent a number of real-life pieces of equipment, including fuel, such drum in refining processes, and settlers, as is the case here. Okay, slide 16. Need to introduce two unit operation. We start with mixer first. Mixer 2. We have three mix 2. What is it? MIBK2. So this is the latest one. Next. So for the MIBK2, it is 50 kg per hour on IBK at 25 degrees C, 1 APM. Okay, there's no warning. MIBK2. And Trimix 2. There, this is the latest one. Inspection. Okay. This is MIBK2. Yes, MIBK2. 50. It's 51. If there's no error, then we need to we will continue to add flash flash 3. Yeah? Yeah. Flash 2. Flash 2. Connect. Don't forget to save. To output, which is FL2 vapor. We have FL2 MBK. FL2 H2O. All right. Next, it asks you for the condition for the flash 2 ATM. Next. Okay, run simulation now. No issues. Go to stream. And you have a lot of stream you are interested in. FN1, FN1H2O and FN2H2O. FN2H2O. Check the mass fraction for water. You see previous separation unit can only achieve like 78% of mass fraction of water. Now we have another one. It increased to 90% fraction. But this is still below the 95% threshold. So what we do now, we can use the design specification study by ASPEN, a tool that allows ASPEN to calculate iteration for obtaining the 95% H2O purity. So this is the optimization part for this process. First, we need to go to the design spec. Design spec is under flow sheeting option. Design spec. At the moment, you need to create new. Okay. Don't forget to save. So our goal is to get the H2O mass fraction. The variable is H2O MF. Specify. It's a stream mass frac. The stream is FL2H2O. Target mix and what component is water. For the spec is H2O MH. Oh, capital letter. Actually, it's similar. H2O MO. Oh, I'm using 0. The target is 0.95 fraction with tolerance of 0.001, very low. H2O MF. Let's see. Oh, okay. Next is the vary tab. The manipulated variable is the mass flow. In this case, we manipulate the MIBK2. MIBK2, it's our component is MIBK. So this is the limit for the iteration. So what ASPEN do is let's see. It's inputting the value starting from 35 first, then slowly increasing it. Record level MIBK2. The line 2 is flow. Since the MABK2 now, the input is around 50 kg per hour. So we try starting from 25 kg per hour, increasing to maximum of 250 kg per hour. So from there, we see when it will, reach the 0.95 percent of H2O in FM to H2O. Next, okay, it's ready. We can run the solution. There's no warning. This is the iteration. 3 iteration, 4, 5, 6. Then only 7 iterations. Okay. Go to the stream. Mm, Before we go to the stream, we go to the conversion. Conversion for the solver 1 result. All right. This is the summary we just do. Okay. 7 iteration. So the best value is 192 kg per hour of MIBK. This is talking about, this is referring to MIBK2 stream. Now we go to the DS1 result. This is the initial value that you do before at 50 kg per hour. We get fraction for the MIBK2 is around 90%. And we do the iteration. And the optimum MIBK flow rate for the MIBK2 stream is 192 kg per hour. We get the 0.95%. So that is how you do the optimization using design spec. Later you will use this for the you can use it for the assignment, the IDP as well, rather than inputting a lot of unit operation or separator to achieve your goal. You can also use this design spec to do the iteration for you. Next is the another, what is it? Example, slide 20. You do that one first to get the 97 purity. I need a coffee. Wait, Okay, continue. So how to determine the 97%? So to do this, we need to go to the input and just change this to 97. Other remain the same. Let's try first. Oh, warning. Outside the bond. All right. So meaning it's not enough, huh? This one. How about this to 500? See, still not enough. Huh? Outside bound. Berapa lah belum? How about 1,000? Oh, okay. No, it's okay. At 1,000. Let's see. Check the conversion result. Okay, only 3 iteration. Value is 556 kg per hour. Yeah, 560 kg per hour. Then let's see the result for design spec. Previous simulation, we do until 500 kg per hour because we limit the maximum is 500. So for at 500, the percentage of water is around 96,853, very close. But still below the 97 for the 0.001 tolerance. Uh, then we system 856 more kg per hour. We get the 97. Okay. All right. Safe. Huh? So to get 96, sorry, 97, you need a lot more MIBK, like I don't know, another 300 to 400 extra kg per hour. Yeah, just to get the 2% increase. One depend on your process. If you really need that 97% quality, then yes, you need that 556 kg per hour. Okay. ASPEN plus distillation. Slide 21. So ASPEN plus distillation under column, we will have three type of distillation: STW, DISTL, and the track. So let's see, okay. So the STW and the ISTL are designed for single feed to output. The STW, this is how it calculate how it perform the simulation. So the STW is based on the Gilliland, Will, and Underwood method for the number of stages and reflux ratio. Meanwhile, the ISTL simulation is based on administer method, and user need to specify the number of theoretical stages, reflux ratio, and overheat product rate. So the simplest one is the STW. The ISTL need more information from the user, and red flag require much more information. So red flag uses rigorous calculation for highly non-ideal solution or process that undergo chemical reaction. User can define multiple feed and product stream. For the ISTL and the STW, it's only one single feed with two output. Red flag is much more accurate. It allows user to simulate random packing, including packing, structured packing, and the column. Because this is a distillation tower, there are column. Even the column you can specify. So at mixer tree of the flash tree, this is connecting the MIBK, MIBK2 with the MIBK, FL2 MIBK, MBK from the flash 2 with we mix it with FL1 MBK from flash 1 into the mixer 3. So continue from the previous example. Oh yeah. Okay. Say, don't forget to say. Mixer 3 here. Should reconnect this one as well. Reconnect. Rearrange. Okay. Then we have premix 3 now. Set, okay, and run. So this is based on the 97%. 97%. Is it 95% or 97? Maybe 97%. So run and check. So far, no error. stream. FN1, FN, sorry, FN2 H2O. Inspection. Yeah. FN1 H2O is 78% last time. And after we do the design spec optimization, reach 97% now. Let's check the trimix, trimix 3. For trimix 3, this is the fraction. Most of it is MIBK. About a percent. To check it out. So next task is to introduce column DSTW. 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 New. DSTW 1. USTW 1. We connect this. DSTW top. DSTW top. This one is DSTW bottom. DSTW H2O. Okay. So make sure the line are connected. It should be like this now. Yeah. Right. Okay. Click next. It will ask you to input the STW spec. So for the spec for the STW, the number of stages is you start with 34 first. Just apply an error. So this is 1 bar. The boiler is 2.5, so 1.4 bar. It's 24 bars. That's right, 24. Sorry, yeah, stages. Acetone, the likely is acetone. How much you want to recover? 0.95 or 99.5%. ABK is the MIBK. One is 0.01, 1%. IBK. Reset and run the simulation. So we get a warning. The warning is lots of wind equation for minimum stages. Remainder of block calculation by pass. Jangan kita dapat inconsistent pre-water setting. Okay. Set the free water to yes at setup. Spec global lah. Spec setup global. Okay. Then free water yes. We run the simulation. Oh, okay. Now it's 36. Apa tadi minta ada? Yes. Error. Okay. 36. This is based on slide 24. Come on. 30M is 25. Oh, this one is okay. 122. 0.995. Oh, aduh. 0.006. Try. Calculation atau generate table with table of practices and tactical stages. Let's see. Reset and run. Tak tahu. Kami mungkin mana dekat spot. Oh, okay. Itu ada masalah sedikit. It need to be added to the condenser. Aduh, lagi. Sekejap. Ya, ada isu. ASPEN. Okay. Oh, no. Aduh, Atik, able to open compound file. File may be corrupt. Uh, itu masalah. Tak lah. Corrupt dah filenya. Hmm. Ya. Okay, this is uh, the last file that I have for the STW. So this is what is it? The spec. Okay. Conversion saturation is 100. Check the report log. Property set, there's no alcohol now. Let's check there. Oh, yeah, stream. Okay. Stream the STW top. Wow. STW top and this STW bottom. Inspection. So my fraction of acetone at the STW top is 0.96. So MIBK bottom. Okay. Next is the reflux ratio versus theoretical stage. This is under block. Go to block, STW. Result. Okay, it's fine. So the trade-off between number of stages in reflux ratio. Okay. The higher this is slide 25. Higher stages will increase the equipment cost, while increase in reflux will end up the operating cost. Oh, yes, correct. This is the trade-off between either you want to increase the stages or you want to increase the reflux. Both will incur cost, but which one is the best? This one is depend on the and process and the cost itself. To do some cost analysis here. All right, now you save, then change the, let me save as, save as, uh, okay. Now we change this to distl. Go to column distl1. distl1. So we connect. This one is reconnect source. Source. Oh. Since we are using a new distribution column, if you click next, it will ask you to enter the spec now. Number 17. Refer to slide 27. The stock ratio is 1.5. This is equal to more ratio is 0.3502. This is 0.8, then 1.2. Reset, then run. Okay. Now we check the stream for order. Masih juga di STW. Okay. Oh, lupa dah tukar. Tutlah. No. When for shift this one. This is the STL. Reset and run. Go to the stream. distl top and distl bottom. Best fraction of acetone. So now the best fraction of acetone top is 96% only, 97%. While MIBK bottom is 1%, very, very close now compared to previous DIS, so DISTW. To save as ASPEN 2025. Okay. So this is for the DISTN. So the difference is see a lot of input compared to previous BOST 12. Then we got to reflect. Okay. Reflect one. We connect on. Oh, salah. Ah, yeah. Red flag require more input. This is step 29, such as refractory ratio and number of vertical stages. Next, yeah, a lot more. Equilibrium, sustain, then this is a total condenser, kettle, boiler, this one vapor liquid. Standard reflux ratio, this one more is 0.9995. Distillate to feed ratio, mole 1.4. Click the fit basis. Click the fit basis to determine which component in fit other component for distillate the fit ratio. This fit and yes. For distillate the fit ratio. Acetone. Our target is acetone. To improve recovery of acetone. Next is okay. Next is stream tap. Oh, siap gitu. Pada. Total can look for the ratio is in mass. One ratio is 1.4. Distillate to fit ratio mole 0.999. 5. This is it is 3 mixed 3 components. Okay. Pasti kena ni lah. So for the stream premix, it enter at stream number 5. Then for the product stream, we have LDFR bottom. It's liquid 10. LDFR top is 1. Next is pressure. Top bottom stage 1 in 0.8. Stage pressure drop is 0.305. Over here. Second. Okay. So under pressure tab, we will simulate a distillation column that is operating at 0.8 bar with 5 millibar drop per stage. So it simply has 10 stage. Okay. Plastic that in real pressure that resists a pressure drop along the column from the bottom, highest pressure to top, lowest pressure which is granted for which for via specifying the stage pressure or column drop pressure. Dapat tak run? Okay, minta je. Product stream with fast liquid is the allowed product stream from stem stages has phase 1. Oh, that is one is fast liquid. When only when basis vehicle liquidated when so mana that LDFR still on it. You second liquid. Oh, okay. Lagi. Component to find second liquid phase. The liquid phase is water. Not lah. Kau ada soalan problem. It's either LDFR bottom, DFR top. Oh, not replacing that. MIBK bottom is, oh, it's reducing. No? It does not, this didn't reach the degree of purity 95% for acetone at the top. Turun ke 83%. Hence, user need to increase the number of stage to 24. Alright. Go to the log. This is to 24 now. With runner ratio of 3.5. The fit will enter a trade flow. Alright. Let's see. Right? Start. Pretty fast. Issue. No warning. Okay. Let's see. Aduh, kena lah yang buka je. Please. It's increasing to 98% now, which is better, higher than 95% target. MIBK is 95%. Still je masih dapat 99 ya. But at least the quality of acetone is more than required. Sorry, more than the target. It was worth mentioning here that since we have in hand a rigorous color model, for example, a design specifications case study can be conducted here where the design spec variable will be the mass fraction of stone in the top target with the target value of 195. Oh, betul. Because it is not mentioning here. Slide 34. It is worth mentioning here that since we have in hand a rigorous color model, a refract model, for example, a design specification case study can be conducted here where the design spec variable will be the restriction of acetone and the top string. Okay, this is just information. If you want to conduct design spec and the optimization, the variable would be the mass fraction of acetone in the top string with a target value of 0.95 and tolerance of 0.001. So here instead of H2O, change it to ASPEN. The method variable will be the block variable, namely the molar refractive ratio. Okay. Let us look at the result for the refract distillation tower. Select the refract distillation under the block. Scroll down until you see the FR subfolder. Click on result. Uh, Result. This window shows the final operating condition. Okay. Yes, the temperature we have heat duty. You can see that in this video, whatever ratio is 3.5. Yeah. You can also see the required condenser conductivity, which is equal to negative 33 prime. 0.97 condenser cooling duty. Berapa condenser cooling duty? Kilowatt. Yes, negative 32, most of negative 33. Of course, the negative sign indicates that heat will be taken off the condenser. How about the boiler of 30 kilowatt? If you select the balance tab at the top of the screen in figure 4.21, you can see the overall heat and material balance for the column. Okay. Applying the overall energy enthalpy balance for an open flow system, we have substituting each value from the box result, summary tab and result balance tab of the dictionary, we have almost zero. You can see the relative difference, meaning this no operation is 100% perfect. So for the energy, H in minus H out plus Q reboiler plus Q condenser. So H in is negative 374. This one is unit of the car, kilowatt. So negative 374 to 94. This one H in, H out, negative 366.636 means like 5.591 plus 40.75 Q reboiler here. Sorry, here. Q reboiler is 40.2811, then plus negative 32. If you do the calculation, H in minus H out plus Q reboiler plus Q condenser, it is equal to 0. Just on the P balance. It's not 0, it's 0.0000, then some number, it's almost 0. Meaning we do this relative different. Finally, under the profile sheet of the track, ASPEN Plus will present a summary of the operating condition for this simulation. Oh, wait. Wait. Okay, this is the TF, TPFQ. You can see the breakdown of the liquid and vapor flow rate from each tray. We have how many tray? 24 tray. So this is the information from each of the tray. Yeah, okay. From the view drop down under PFQ, you may select all or subset of a profile summary like summary fit and product stage flow and hit the T enthalpy define. Okay, here, yeah, summary, fit, stage flow, T, and all. Design and specify column internal. For the sake of getting realistic design data for the geometrical specification, this is slide 38. The mass production capacity have been multiplied by a factor of 10 to mimic real industry chemical plant. Okay. Back to the main flow sheet. As pointed out earlier, the design aspect of the column internal can be dealt with under red flag block. Okay, the missing hydraulic data will pop up asking to generate the hydraulic. Okay, here go to configuration. Under configuration, there's a design and specify column internal. The missing hydraulic data will pop up asking to generate the hydraulic data. Following, click on generate button to initiate the process of entering hydraulic data. This one. Machine is missing hydraulic data requiring for column sizing and rating. Click generate to run the simulation. Calculate this data. Click OK. Just to generate. Okay. Under section tab, this one, you may click either add new or auto section. Here, add new or auto section. To create one or more section, the word section in this regard means a set of column tray that will be treated equally as that as they all have the same geometrical and hydraulic spec. Let us click the auto section button and then select based on fit or draw location. Okay. Based on fit and draw location. Right. So figure 4. Okay, it's created two sections, one above the feed tray. Yes, correct. Another below it. So we have CS1, CS2 now. Noted that the feed stream tray mix tray enter as a liquid mixture above stage 12. Okay. From the top tower, you see. However, the user must enter some geometrical parameters like tray spacing and diameter. However, such initially entered are subject to change as long as the safe version conditions are not met. Click next button and run the simulation. Next button, run the simulation. Go to INT1 hydraulic flow. Okay, INT1 hydraulic flow. Oh, okay, this is the hydraulic flow. Safe, huh? Select stages with error or warning. Stages with error or warning kat bawah. Berapa banyak? 2 sampai 11. See what type of error or warning are there. The simulator show that there are problem with the first section 2 to 11. The warning said that the liquid rate at any stage between 2 and 11 is either below or approaching what is required by the specified minimum weigh loading of 4.471. Yeah, liquids. The total liquid rate for stage 2 is below what is required by the specified minimum weigh loading of 4.471 cubic meter per hour meter. This is the minimum acceptable volumetric flow rate. This is slide 42. Okay. This is the minimum acceptable volumetric flow rate of aerated liquid per unit length of way, calculated on the basis of total liquid flow divided by total way length. The default is 0.5 gallon per minute per inch. For a given liquid flow rate, the user is left by modifying the geometrical spec of the tray. So it will be an exercise for the user to manipulate tray parameter like tray type, bubble cap versus C, set down common length, weigh height, tray diameter, and tray spacing. Figure 4.24, where to make the changes such that you end up with 0 warning. Tekan geometry. 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 This is based on CS1. Yes. 2 to 11. Okay. 2 11. Okay, CS1. Oh, banyak eh. Oh, see. The cardboard arrangement is conventional. Number of faces is yeah, 1. Okay, 1. The whole diameter is 0.0127. Okay. Huh? Oh, okay. Subdiagonal width the curve. All is 0.1. The thickness 10 kg. This one is meter. Because about oh, China 0.0405. 0.0405. Diameter is 3 and 2.812. Masih dapat kan? 0.272. Sudah. Okay. Finally, figure 4.25 show the result in terms of column width, number of two, table height, and page drop. Oh, that run. Alright. Oh, makin teruk. Jadi warning dah. H2 is operating at 110% jet lag. Okay. I will try to drop. Makin masalah. No, kasih lah. 2 to 11. Ah, tempat dia. Lepas tu, betul. Oh, stuck. Oh, beratnya. Seperti itu. Hmm. Stage with warning and cool level. Okay. Nah, dia mahu luka tu. 0.0405 tu. Out of range. Cek. 3.0. Oh, sama dengan 3.0. 0.05. Okay. Sama dia. Hmm. So, wow, what if? Dah, dah, belum. Okay. Hmm. Sekejap. Alright. Alamak, masih juga. Itu pasti dah. Next is go to the column hydraulic result. So in the column hydraulic result, we have how many number of tray, 22, the total height. This is information about the column, specifically the tray. This, this is the pressure drop for the tray. Okay, ini ada masalah. How about CS2? Choosing 23 to 32. Coba tak betul. Oh, semua tak. Oh, oh, this is just a warning. So, stage 2 to 11, at least. Okay. Next, slide to 45. Oh, habis dah. It's an exercise. Mixture of cyclohexane, toluene will be separated using station to its component with the highest possible quality. Okay. The feed stream having a flow rate of. Oh, okay. Oh, this one. I can do this. Yeah. This is using a rectific unit. Oh, I think that's all. Okay. We continue vector next week.